Hello, my name is Caio. I am a power engineer at Elipse Software. Today, I'm going to present you to the Elipse Software self-healing module. Elipse is a software solution developer for automation and energy management. We are a global software company and leader in the Brazilian power market. We have been working since 1986 in automation systems, have offices in Brazil, USA, and Taiwan, partners in more than 30 countries, and already have more than 50,000 systems installed. We have a dedicated and specialized support in the energy sector, a wide network of distributors and integrators around the world. We focus in constant product evolution. We have great experience and knowledge in planning, developing, maintaining supervision and control systems. We also provide a quality assurance service, which is a constant monitoring of projects and applications since the basis through its conception and development. This ensures the best development practices in the market. And Elipse Software has the international certificate DNV-KIMA, which attests the compliance of the software and communication driver on meeting the requirements of the norm IEC 61850. Our energy solutions are segmented by specific markets such as substation automation, advanced distribution management systems, energy management systems, generation management systems, electro-intensive industries, smart metering, and data collection for protection, or oscillography. Here are some of our clients. We have provided a wide range of solutions to these customers. There are utilities companies, transmission companies, and generation companies among this group. We highlight Petrobras, Brookfield Renewable Energy Group, and Tractebel Suez. Elipse's portfolio of energy products is contemplated by Elipse Power HMI for substation automation, Elipse Power Gateway for protocol translations, Elipse Power ADMS, which is the Advanced Distribution Management System, Elipse Power EMS, which is the tool for operation of transmission and sub-transmission centers, Elipse E3 for power generation plants, Elipse Power Industry, and Elipse Power AMI, which is smart metering solutions. So here we start the contextualization of our problem. Today, the socio-economic development of a country depends directly on the effectiveness, safety, and reliability of its electrical systems operations. Because outages represent great costs and losses to their business, consumers are each day more demanding in relation to the quality of energy being provided to them, thus putting big pressure over the reliability indexes of the utilities companies. Therefore, some of the main problems power utilities face today are the maintenance of thin costs, the replacement of damaged devices, and the consumer's dissatisfaction. Under that perspective, permanent faults are the main cause of losses for both utilities and the society. It is required a significant amount of time and effort for field teams to reach and restore the power service. That's why solutions to mitigate the effects of power outages are always being sought in the market. From this point of view, we have a framework of great challenges today. First, there is the need to improve the network availability. Because utilities usually have a large number and duration of outages, this means bad continuity indexes, financial penalties imposed by regulatory agencies, and losses due to the time not supplying energy, not to mention the dissatisfaction of consumers. Second of all, it is difficult to quickly, safely, and stably execute maneuvers to restore the healthy segments of the network. We have the risk of undue re-energizations capable of threatening the security of maintenance field teams. Also, it can occur the violation of device operational limits due to the different demand of energy throughout the day, causing other defects along the feeders. Every operation has to be planned so that the protection system can be re-coordinated after load transfers in order to detect new faults and avoid erroneous actuations. Therefore, it is required complex logic implementations and more commissioning time. Also, traditional self-healing systems have a great amount of distributed logics in devices over the network, so any network changes necessitate local adjustments on each automation field equipment. Thus, this number and complexity of distributed logics implicates in many firmware updates and demand time and travels along the feeders until the entire system is updated. It is invested a lot of time and people to configure the system and get around the problem to restore the electrical grid. Also, the high costs of implementation, maintenance, and expansion are extremely inconvenient to utilities, and thus they need to reduce their expenses with maintenance teams. Last but not least, there is the dependency to hardware manufacturers. Because regular solutions are exclusively linked to hardware equipment, their lifetime are trapped to the same as of the hardwares. So the solution is susceptible to mechanical defects and suffers depreciation and needs to be replaced or specially cared for frequently. Utilities do not want to be detained from choosing different types of equipment at more competitive prices, nor want to be held from using a more convenient mean of communication or protocol. The need to protect their investments against depreciation and technological gaps are a constant worry. So what we propose is a self-healing application that runs as a module in the Elipse Power software. Elipse Power has its operation based on the standard IEC 61970, the Common Information Model. This ensures the same structure base for every application built in this platform, allowing the easiness of use and less dependency on programmers, the automatic generation of screens and operation diagrams, and the definition over the same graphical interface of objects, electric configurations, and connectivity structures. The electrical model is the main component of Elipse Power. Based on it, all other functionalities are integrated to form a unique solution. So we have SCADA, an auxiliary feature that brings the real-time information about the state of the electrical system, updating the solution to the real conditions of the network and making it possible to quickly decide the best set of reliable actions. The gateway feature that enables the interoperability between centers and different equipment protocols, and the electrical modules, which are algorithms aimed to work on specific points over the electrical model of the system. As an example, we have the self-healing model, which proposes an automatism able to isolate and reestablish loads using all the versatility and reliability of the platform Elipse Power. So, as said before, everything starts with the electric modeling of the system. By that, it is possible the definition of the network through an electric CAD editor that lets describe the electrical equipment parameters and the connectivity between them. The generated database is the heart of all other models, allowing the tool to configure the screens in very little time and with minimal user intervention, and the information can be grouped into data objects, facilitating the management of the information. This provides shorter commissioning and system configuration, as well as lower maintenance costs and more reliability. Through the standardization of the electric model by the IEC 61970 SIN standard, you can set all the parameters of the device evenly and ordered. Commands, measures, protections, and terminal states are always organized in the same way, in the same positions, and therefore are easily accessible to any user. This definition of a single pattern provides better ease of understanding the projects and smaller dependency of programmers. And here we have how the self-healing algorithm works. For start, the trigger input for beginning is the signalization of either a lockout, lack of voltage, or overload in any equipment, be it reclosers or breakers. Lockout means that the recloser has exhausted all its attempts to restore the circuit. This often happens when there is a permanent fault on the network. And while the lack of voltage indications helps to identify substation shutdowns and allows their respective loads to be transferred to another source, the overload monitoring grants that the network stability won't be jeopardized at destabilizing events. Then, the algorithm calculates all the operations required to minimize the de-energized load. It aims for the higher amount of load or amperes that it can restore. In addition to that, it calculates the current that will pass on each device after its actuation in order to keep the system at stable operation and transfer the largest amount of load to other feeders. Then it waits the confirmation of command actuation before continuing the sequence. In other words, the device has to respond on whether the solicited action was indeed executed. This is a matter of reliability so that the operator has the certainty that the actions were really taken in the field. If any unexpected performance are identified, it aborts the procedure and waits to the maintenance teams to resolve the problem. That could be any topological changes or protection actuation. This is more of a conservative policy for the solution actuation. Another point is that the scripts enable flexible actions in each stage. For each state value of the switch device, open or closed, it is set a protection profile in order to keep the protection system running accordingly. So it is made a comparison between the configured and the field value to decide on which is the appropriate profile. Before the self-healing maneuver starts, each equipment is checked for operation availability. It takes into consideration if the equipment is available to participate in the self-healing. If it's not, it is considered as a continuous wire, as if there were nothing there. So, if it is desired to have a hotline tagging on any branch of the feeder, it is simply a question of not letting the specific branch to participate. The self-healing can be operated under two distinct architectures. The first refers to the model inside the Elipse Power HMI solution. In this case, it is possible to perform the network recovery by the connection to the distribution devices through protocols like DNP3 or IEC 104 and fiber optics or GPRS networks. This is a more viable setting from the point of view of systems that already have contingency sites and local operation, being the communication with the control center made by the gateway interface at Elipse Power HMI. This already is an architecture with self-healing integrated to the control center. It is a more robust option because it can make use of the information on GIS and OMS systems, and as we shall see, there can be achieved many benefits from it. So, as benefits, we have the improvement of continuity indicators, the reduction of maintenance team costs, the reduction in commercialization losses due to outages. We have less implantation, maintenance, and expansion costs, and the preservation of past and future investments. The automation of network restoration is the reason of continuity index's improvement. It occurs by two ways. Firstly, by the decrease in the average, maximum, and individual length of outages due to the faster automated recovery of healthy branches. And secondly, by the decrease in the average and individual frequency of interruptions due to the rapid restore of problem-free segments in less than 5 minutes for most cases, thus not characterizing infractions by regulatory agencies. Then, there is the command interlocks that are based on the topological state of the network, on the communication system state, on the availability of equipment and segments in maintenance that prevents re-energizations and so guaranteeing the safety of field teams working on the grid. The analysis of the electrical model is a feature that allows a fast and safe execution of maneuvers in real time. Any violation on device's operational limits are easily identified by the algorithm, and that makes it possible to stably transfer loads to nearby feeders. Also, the actions taken by the self-healing can significantly change the topology of the system. So, there is the need to rearrange the protection in order to recoordinate the system. The ease generated by the electric network model allows the solution adequacy to specific needs, such as the customization of synchronous closure of switches and hotline tagging. Therefore, a self-healing solution guarantees, besides the greater availability of loads, robustness and reliability of operations, the avoid of maneuvers that would generate other sources of faults throughout the day. To summarize, we have better indexes of continuity because the automation of restoration, in conjunction with the electrical network analysis, represents immediate maneuvers that maintains the largest number of consumers connected, and we have increased security in control actions because the transfers are more reliable and will not cause overloads to the system along the day. The solution interoperability is another differential for Elipse's self-healing module. Because of its adaptability and vast variety of communication drivers, it grants the freedom of choice to any equipment of any hardware manufacturer, including the means and protocols of communication. Also, it enables the use of existing infrastructures. Since there is no more a solution exclusivity, the problem of legacy equipment emergence can be surpassed. The investments can be preserved over time because the solution does not suffer depreciation, and the maintenance and expansion are much less costly compared to the hardware solutions. Value is added to the software. As benefits, we have lower costs of replacement and expansion of field equipment. It is not necessary to buy new software solutions. More competitive prices for energy utilities at expansions and systems replacements because the software opens the possibility to many proposers to compete, and reduced initial investment by making use of the already existing infrastructure. The centralization of self-healing solutions at Elipse Power allows the entire maintenance and commissioning of points to be done in one place. This represents a lower number of equipment that require logical, firmware or operational system updates. By consequence, decreases in the cost of maintenance teams with logical configuration and equipment are achieved. There's only left simple logic to be implemented at field equipment. So we have the reduction with field team costs, the shorter system deployment time, and the reduction of commissioning costs. The integration with gel reference G systems allow automatic updates of the network topology, so there is no need to do this manually. This allows for the rapid identification of which devices should be operated, saving time and resources for utilities to start examining the maneuvers that will be performed. The integration with OMS systems enable the identification of non-automated switch states. This permits the self-healing to take into consideration the best electrical paths available in the network according to the real-time topological state of the system. Our benefits are the shorter time for system recovery, because operators don't need to study diagrams before executing maneuvers. The system does it automatically. The greater assertiveness over the best paths to restoration by the identification of each manual switches are closed and can be used or not. And the greater assertiveness of our recomposition process, since all the best available branches are used and a potentially higher number of loads can be restored. Another point is the integration of system simulators, like PowerFlow, which makes it possible to evaluate different scenarios and future behaviors or past of the self-healing solution. It is of great significance knowing previously what are the actions that will be taken by the algorithm, or the ones that were taken, having communication or mechanical problems, or even failures of operations, and test those scenarios to be prepared to take the necessary measures. It is also obtain a greater reduction in commissioning systems. Elipse has a team dedicated to the constant development of new protocols and interface with several other systems, so that new features are fully compatible and natively incorporated into the existing platforms. As an example, we have the capability of aggregation of equipment such as fault path indicators, FPIs. This ensures the preservation of future investments because technologies will not be lost. On the contrary, they will be always serving as the basis for the next technological tendency or level. Now, I'll give you an example of how the system works. Here, we have a model grid in which we have 4 feeders in an interconnected system. Red means the breaker or recloser is closed or energized. A permanent fault occurred in the distribution grid will cause an outage not only on the faulty load section, but also to all subsequent loads from the point of problem. For example, a fault at load 9 would turn off also loads 8 and 7 without having any problem on their specific lines. To circumvent this problem, it is required a maintenance team to analyze and physically operate the necessary maneuvers for isolation and recomposition. This is a highly unwelcome problem because in several similar situations, loads that could be in service are lost, if only they were energized fast and securely enough through other feeders. So, simulating the fault, this is what happens. The system will perform the AC reclosing relay protection ANSI 79 so that the system is restored automatically, being the case of a transient fault. In general, the relay attempts 3 or 4 times to close with increasing timings at each step. If those recloses are not accepted, the ANSI 79 protection enters in lockout, preventing that the respective device is rearmed automatically. It is when the self-healing enters in action to isolate the problematic region and recover the highest number of loads possible. In the case here, it was simulated a permanent fault between load 9 and G4. Note that all the respective loads are de-energized at the feeder. So, what the self-healing does is transfer the load 7 and 8 to feeder G3. Note that load 5 was de-energized so that the feeder G3 could feed the other 2 loads. The next step would be passing these unassisted loads to G2 and so on. We highlight the fact that the solution does all calculations at computational speed before the start of operations. Thus, the proposal of self-healing is re-energize the maximum amount of power over healthy sections of the feeders through alternative paths in the grid. Finally, here's a video that enlightens the solution operation. We simulate a lockout at breaker 4 in load 9. The self-healing isolates the problem by opening recloser 7. Then disconnects load 5 so that G3 can take both load 7 and 8. Since it calculated that the nearby feeders could take the additional load, it goes transferring all of them in sequence. Resting only load 9 de-energized, since it needs field teams to physically recover that branch. Elipse Software thanks you for your attention and hopes you have reached your expectations about our product. For more information, please contact our local distributor or the email power@elipse.com.br.